Hi folks, and welcome back for what is now going to be part one of my Digital Sky project videos, even though it's the second video. This is the one where I'm actually going to explain what the project's all about, what I'm trying to achieve here. But before I get stuck into that, I thought I'd just say thank you very much to all of you for making me feel welcome back here again. It was really nice seeing people in the comments that I haven't seen for, a year and a half or so. At the time I'm recording this, there's like 11 people that I haven't replied to. Sorry, I thought you'd probably prefer it if I actually spent the time making this than saying hi. So as a group to everyone, hi everyone, really nice to see you again. I have actually kind of missed the interaction, even though I'm not replying to you. Anyway, let's get stuck into what Digital Sky is all about. What am I trying to do here? I have a lot of different light sources in my little man cave, kind of amber coloured lighting for the evening when I'm watching TV. Bit of general background lighting with LEDs on the ceiling, all manner of different task lighting for when I'm doing electronics, different lighting for when I'm filming, but all in all it's a bit unsatisfactory and quite often not bright enough even with all of that, and especially in the winter time when the sky's so grey, I find a bit of sad lamp blue helps out. Now what I'd really like on the ceiling is this. If you're at all interested in hobby electronics, there's a fair chance you already know what an individually addressable RGB LED, or sometimes known as a NeoPixel, is. But that's what we're looking at on the screen at the moment. So this is the little microcontroller built into each LED, and we're zoomed right in there. And I'll just zoom out there a bit so we can get a look at the whole thing a bit better. There we are. So that's a single LED there, and I'll just move over to one that's actually lit up at the moment. Should be next one over. There we are. So you can see the individual red, green and blue elements there. So the little microcontroller you were just looking at was one of the pixels on this LED matrix board. I got these at about August last year. At the time they were about 12 quid a piece. I just checked now, they're about a £5 a piece on eBay now, so really coming down in price. But gives you 8x8 64 LEDs per board, and it lets you mix RG and B to get any colour you want, including white. And when you crank the brightness up, these are running on about a quarter brightness at the moment, they put out a reasonable but not amazing amount of light. But the kind of my problem with these really is the cost would be very high for what I'm looking, because I really want like daytime levels of brightness in here, so I'm looking for quite a lot of light output. And the white that they put out, because it's a mixed RGB, isn't really a good quality white, and I'm looking for a good quality white light, so I thought I'd try some other options. Okay, so now we're looking at a very similar microcontroller from another LED module. If you're quick at counting up, you'll notice that there's an extra wire on the output, so we're driving an additional channel over here to what we were before. So we'll just zoom out and have a better look at this. Looking at the thing zoomed out now, we can see on the left hand side we've still got the RG and B pixels that we had before, LEDs that we had before. But now over on the right hand side we've got this big yellow smiley face, and that's the phosphor coating on the warm white chip that's inside this one. These are available RGB white or RGB warm white, so I thought I'd try out one of the warm white strips. So this is a strip of the RGBW LEDs, got one every 3 centimetres I think is the spacing on them. And here is a similar set of the same RGBW LEDs draped up and over the ceiling. So see, red, green and blue's not bad. and then coming in a minute we've got the warm white will come along, and next across we've got warm white plus RG and B. And when this is happening, I'll just turn the camera a bit, but you'll notice as this works its way down to the left hand side, it ends up kind of orange in colour, and that's because the voltage is sagging and the blue light, the blue LED, needs a higher voltage to turn on than the red, so everything ends up red tinted. And yeah, I mean, it's pulling quite a lot of current, so it's like, I think it's about 60 milliamps per individual element, and there's 300, so it adds up to a few amps to drive the whole strip. So the code that's driving this strip is really quite straightforward. All of this bit you can ignore, it's just initializing the LED strip and telling it how it's configured on the Raspberry Pi. This bit here is opening an image file, resizing it to be the same number of pixels in our strip, which in our case is 300 because it's an uncut strip, and converting that into an array of numbers so that we can actually process it later on. And then down here we're just going through each row in the image one line at a time, and then for each pixel within that range, within that row, we then get the red, green and blue values and we send it out to the strip, and then we just repeat that. So we're working our way down the image one line at a time. And the obvious next stage to doing RGB for the pixels is throwing in a bit of white to the mix. So this is subtracting red from blue, so whenever there's clouds in the sky I figured it's going to be full RGB to give white, so red will be high at that point, so when red minus blue would go down to something close to 0, so when there's clouds in the sky it should get a bit darker in here, and when it's all blue sky and there's very little red in it, it should be a lot brighter. But the problem is now we've got so much voltage sag across there that it's getting hard to actually choose the colours and work out what's going on. And it's not surprising because the strip is pulling close to 30 watts. These RGB warm white strips really are a lot of fun and are pretty good. But as you can see, the problem is pulling nearly 30 watts for a strip. That's 6 amps trying to flow through here. So they're really not suited for that kind of longer run. You know, they came on a 5-meter reel, 300 LEDs, but you need to pump power in at both ends, or possibly even 3 or 4 places along the way to run them all on 5 volts. Now, while I was playing around with these, Matt on DIY Perks put out a video about making some new lights for his studio, and he used these high CRI LED strips, and I've been waiting for ages for these to come around because they've been available as expensive things for kind of storefront lighting and shop displays and things like that. But yeah, finally the CRI 95 LED strips are out and reasonably priced. So I got myself some daylight white, natural white, warm white and a nice ice blue, which is a beautiful sky blue colour. Though it probably doesn't really show up in camera, rather conveniently these blue Marswall ice blue ones seem to be pretty much exactly the same wavelength as the Philips sad lamp thing, so hopefully that'll keep away the winter blues as well. So with the combination of the RGB warm white, the 3 different daylight ones and the ice blue, I reckon I've got just about every colour that the sky could possibly throw at me. I should be able to match, I reckon, any kind of colour tone for different daylight conditions with a really good colour rendition. Also I've got something like about 120 watts worth of LEDs there, which should give me decent brightness levels for recording, and particularly for working with electronics and trying to work out resistor colour codes on tiny little resistors. When you're in yellow light it's quite fiddly. So next problem is, how do we actually get it all stuck on the ceiling? So 5 strips of LEDs together seems to be almost a perfect fit for the 60mm gaps at the top of the beams in my ceiling. So that gives me, I think it's 7 spots along where I can put in a lamp like that, and that'll be nicely out of the way, and I can daisy chain them together to run it all the way down to the end. So this is my little prototype test light unit. It's just 5 of the strips. I've got a sheet of aluminium. It's got a bunch of heat sinks stuck on it, 2mm thick aluminium to help dissipate the heat a bit. This unit can pull somewhere close to 40 watts when everything's fully turned on. And with 7 of those down each side of the beam, that gives me potentially 14 of these units, which 14 times 40 watts is something like 560 watts of LED lighting, which you know, that's getting close to something like 4 kilowatts of conventional filament lighting. So that should give me a humongous amount of light available. I won't necessarily have it at that level ever, but just to have the flexibility of daylight, neutral, warm white, sky blue, or any of the softer reds and greens and blues for evening colours. So I'm hoping that'll give me enough to feel like it's under a natural sky. So just working out the power consumption for all of this. So here's a rough thing. We've got a bunch of beams on the ceilings with a bunch of lamps in between them. I've got 7 slots where the lamps can go on each side of that big central beam. So that'll give me 7 to work with. And then just measuring the current consumption of each of the strips in turns, it gives me 27 daylight white LEDs, which are pulling 780 milliamps. 27 natural white pull 730 milliamps. The warm white are pulling 700 milliamps. The ice blue are pulling 450 milliamps. And the RGB warm white at 5 volts pull a maximum of 1.35 amps. So totaling all of that up together, that's giving me 2.66 amps at 12 volts, 1.35 amps at 5 volts, making 38.67 watts in total for each lamp. So working that out for 7 lamps and just multiplying all of those things by 7, that gives us 18.62 amps if we want to run it at 12 volts, 9.45 amps at 5 volts. And we've got to get a total of 271 watts of power to power all of the lights together. Now 271 watts is actually quite a lot to be doing at 12 volts, and to avoid using thick cables, because I've got to somehow get the wires routed between each lights, I thought, well, if I can double the voltage, I half the current. So 24 volts at 10 amps gives us 240 watts, which is pretty close to that 271 watts we're trying to get. Or if I went up to 13 amp rated cabling, which is very common and easy to get in the UK, that gives me potentially 312 watts of power that I can distribute with a single 3-core cable. So this is why I'm going with 24 volts as a power rail to run everything else off. I did consider going higher and going up to 48 volts, but then you find that buck regulators and ready-made voltage converters become harder to get hold of. So 20 volts or so seemed to be a happy number that got me sensible connectors, sensible cabling. No, it should be fairly easy to work with, and the power supply modules are dirt cheap. Okay, so we've worked out how we're going to get power to each of the lamp modules, but now we need to work out how we're actually going to control the lights being on and off in each one, or dimmed in each one. So I thought it was worth just giving a quick rundown over the difference between the 12 volt strips and the 5 volt RGB warm white strip in terms of how they're actually set up. So if you look at these 12 volt strips, you'll see they've got cut marks every now and again, so one there and one there. And in between each set of cut marks, we've got 1, 2, 3 LEDs and a resistor, and that's just repeated every 3 positions. So as a schematic, this looks something like this. We've got 12 volts coming in through 3 LEDs and a resistor to ground, and then that's just repeated in parallel. So on our 27 LED wide strip, we've got 9 sets of 3 LEDs in series. And to control that, we basically just use like an N-channel FET or NPN transistor or something like that. We can pull that signal down to ground to turn all the LEDs on, and when we switch it off, the LEDs go off. So we need pulse width modulation, frequency control from some kind of microcontroller so we can adjust the brightness. The RGB warm white or NeoPixel ones work totally differently. So they've got a 5 volt rail that goes to every single LED and a ground rail that goes to every single LED. And then they've got a data stream that goes in to the little microcontroller that we saw under the microscope earlier on, and that controls the 4 individual LEDs within that package, and then that sends data out to the next one and the next one, so on and so forth. And I think you can have something like 1024 of these in series. And this data that they're sending in is an 800 kilohertz NRZ, which is non-return to zero data stream. It's a special way of encoding data so that you don't need a clock signal as well. So this is a look at what we know we've got inside our lamp module now. So we already worked out we're going to need a 12 volt step down and a 5 volt step down to power the 12 volt strips and 5 volt strips respectively. We're going to need some kind of microcontroller and a bunch of transistors to control the 12 volt strips. But for our 5 volt strip we can just feed data in at one end of the lamp and out at the other. So I started to think about what we could do and how this microcontroller would work, because if we're daisy chaining these lights, we're going to need some microcontroller data in and a microcontroller data out. So I started to wonder about what was the best way to implement that and whether to do that on an Arduino or just try and work out what kind of processing we'd need on these lamps. Now at this point I think it's worth a little explanation on what's going on inside the RGB addressable LEDs. So there's a thing in electronics called a shift register, and the best analogy I can come up with is it's like one of those Newton Cradle's desk toys with all the swinging balls, and when you swing a ball and it hits at one end, it knocks the ball out at the other end. And this is the same kind of thing going on. This is a shift register, so we're feeding in bits of data from this side, and every time a new bit of data arrives it pushes the ball out the other end, and as more and more data arrives it gets pushed over and over, further and further to the right. So we go 8 bits of data for the red pixel, then for the green pixel, then for the blue pixel, then for the white pixel, and then we feed the data on over to the next one. And whenever the data stops moving, so when there's been no new data coming in on that non-return to zero 800 kilohertz protocol thing for a few milliseconds, that data gets latched and everything that's up the top here gets copied down to another set of registers, and those are used to control pulse width modulation, frequency control, basically do brightness control for each of the red, green and blue and white LEDs in turn. So I started to think that given that I've got data coming in and data going out, I wonder if I could use a little PIC microcontroller or something like that to decode the data stream from the RGB LEDs. But when I started to think about it properly, this data stream is changing 800,000 times a second. So if I used a 16 megahertz microcontroller, that only actually gives me 20 instructions to decode the data stream coming in and work out how to change the control for these LED strips or generate PWM signals for these LED strips before the next data packet arrives. And 20 instructions in machine language isn't a lot, especially when you're trying to time the arrival of zeros and ones. So I was thinking we need a microcontroller that can control 4 transistors for controlling LED strips, that takes data in and data out, and inside every single LED we've got a microcontroller doing exactly the job we need to do to control these 12 volt strips. So I started to wonder if it was possible to find the little microcontroller inside each of the LEDs as a separate standalone package. And the answer was nearly, but not quite. So this was the 4-channel RGB white or RGB warm white addressable LED, and I couldn't find the chip inside there. That chip's a World Semi 2812B. But I did manage to find its predecessor, the 2811, which only does RG and B channels, but they're cheap as chips. So my reasoning is that 3 lots of 4 is the same as 4 lots of 3. And if we're just sending in a stream of bits here, each of these 4-channel RGBW ones takes 32 bits. Each of the 3-channel RGB ones takes 24 bits, but 3 of those in series is exactly the same as 4 of those in series. We clock through 96 bits of data. So here's version 1 of the breadboard electronics, which was first one. So here are the little WS2811 chips that I was talking about. This is our data coming in from our PIC microcontroller, or Arduino, Raspberry Pi, something like that. Feeds into the first chip, goes through the shift registers, into the second chip, third chip, fourth chip, and then we come out and feed the RGB strips. And in the meantime, the signals from these 4 chips that are expecting to drive LEDs. Now, although we've got 24 bits worth of, 3, 6, 9, we've got 12 LEDs worth there. We're only actually caring about 4 of them. So I've got 4 pull-up resistors, going to a CMOS inverter chip, and that then goes round and drives the MOSFET driver board, which does the 12 volt LED strips. And that all seemed to work pretty well on breadboard. So at that point I thought it was high time I got around to ordering some printed circuit boards. So that's been a bit of a recap on everything that's happened from August, September when this project got started till now in the middle of January when I've got my printed circuit boards produced and actually soldered the first one together. I still haven't investigated why this flickering is happening, but as this video is going to be over 20 minutes long already and has taken me a full day and a half, like literally 20 hours of putting this together, debugging what's wrong with this will be in the next video in part 2. Okay, so that's it for part 1. Thanks for stopping by. It's been a long video, but it does cover 4 and a bit months worth of work on this project. So hope you understand what I'm trying to do here, what I'm trying to achieve, why I'm calling it Digital Sky, and hopefully you liked it enough to come back and see what happens in part 2. Anyway, thanks for watching folks, and see you next time. Bye.